Last session we talked about, one is about finding partition number. Okay, and in that we talked about how do we handle like permutation issues, and designed an DP which was first n cube, and then we went from n cube to order n square. Okay, after that we talked about maximum sum subarray. It's a very standard problem, and in that there is a standard order in cadence algorithm, but we talked about the DP idea for subarray by extending the best answer that ends at index I. Okay, then we talked about the knapsacks. In that we talked about the 0-1 version, and then infinite supply version. Okay, so in 0-1, so we discussed about states of these, and both of them could be solved in n into w, where n is the number of items and w is the total weight. Okay, and we talked about how to change the states in case if a particular item has infinite supply available, right? That we keep at the same state the I and just reduce the weight by 1, right? Then we talked about LIS in details, the order n square DP, and then after few observations we could find order n log n lower bound based approach, right? And we also talked about one particular problem at the end, which is like when you have unique elements in LCS, how do we reduce to LIS? Okay, now this is some problem which we'll take up today. We did not discuss what LCS is and how do we solve it in general, but we talked about we have to find longest common subsequence. Let's start with discussing what is the longest common subsequence of any two general strings where duplicates are allowed. Okay, now what is this LCS problem, or this is also very standard, called longest common subsequence. So it basically says that you have two strings S1 and S2, and you need to find the longest common subsequence. Longest common subsequence of two strings. So in this case, subsequence means non-continuous, and you need to take like elements which are non-continuous in either of them, and they appear in the same order. That's the thing. Okay. This could have been non-consecutive as well, but it can be consecutive as well. Both are allowed, and this you just take subsequences from both of them, and they should be equal, right? So find out such longest such length which exists in the two strings. Okay. Now this is a, if we don't have like the property that every element is unique, so we cannot reduce it to LIS, and hence for these kind of problems we just have one approach, that is DP. And DP for this type of problems where you have two strings and you have to compute some sort of number based on two strings, states always remain the more or less same, which is DP of I comma j. Okay, which means what is the answer or LCS, okay, in this case, of S1 of 0 to I, okay, and S2 0 to j. Okay, so which basically means, let's say we are talking about some index I over here and j over here. Okay, so if this is I and this is j, so basically dp of I comma j will mean what is the longest common subsequence of a b e f and a b f e a, okay, of these two strings. Like this is I and this is j. Now how do we compute this dp of I comma j? That's based on what the end values are. So in this type of states, when we have I and j and we have like two markers that we're doing on two strings, so we can move either of the marker one step back, because when we are calculating dp of I comma j, we will assume that the smaller substances has the solution ready made. So we can call dp of I minus 1 comma anything, or dp of anything comma j minus 1, right? These are smaller instances of the same problem, so we know already, assume that we know their small solutions, and with that, from this particular state we can find out, we can do some transitions and find out into smallest one what can be a potential answer, right? So in this particular state, let's say this particular two strings has this I and this j marked. Okay, now there are few possibilities that, let's say these two characters that they're currently pointing at, they match. Okay, let's say they both match, or they don't match. There are only two possibilities, right? I is pointing at a character, j is pointing at a character. Yeah, that's also possible, but we won't be using that. Like, that's not necessarily smaller at all cases, but we can create in that fashion if you want to. Yeah, that's also ready true. So I will explain when to you, like how do you know that what is ready and what is not, but after this. But let's first talk about this particular problem, that when I and j are at these two indexes, we know that either these two values are same or not, right? Now let's say we are trying to build some LCS answer. Okay, what is the answer that we want to build? This is answer in building. Okay, now let's say these are not same. So of course we cannot append this particular answer to the end and then find the smaller answers over here, right? So these two are not same. So what we can do is either we can, so these two will not match for sure. Now, if these two don't match, either things will be from this particular state, or if you think about it, this particular state. That is, either we will ignore f because f is not going to match with a or anything else, or a will get ignored and everything else, like this all over here. Sorry. Or else a gets ignored at the end over here and all these things are taken into consideration. Okay, these are only two possibilities, because if these two don't match, either of them have to lose their potential to match with anything after this, because it's last character, right? It's not matching with this. If it matches with this, that means f does not match with anything, right? If you think about it, f and a don't match. If they don't match, okay, now if a matches with something here over here, then f has to match after this only, like after a only. But in this particular problem, like in this I comma j problem, right, the way we have defined it, there is no more character over here, so f is going to render useless, right? So in that case, these are only two transitions in which we can go into, right? That either f is going to get removed or a is going to get removed, okay, if they don't match with each other. Now let's talk about another instance of the problem. Like, let's one more state that we talk about. Let's say this is over here and this is over here, so that we want to make the characters same. Okay, so now let's write the, okay, these type. So now these are the 2 pointers I and j. Makes sense. Now in this case, of course, this is a possibility that we do not match it with this, but in this particular case, this is matching, right? These two characters are matching in the two strings. So we can say that whatever is the longest common subsequence of this, that is, there is a possibility that it can be longest common subsequence of AB and ABF, whatever the answer for this is, plus concatenated with E, right? Because whatever you get the answer from this particular part, we can append E at the end, because these are matching. So we can take it as a subsequence and take it as the end character of the subsequence, and then again find the smaller answers from these things, right? Is this making sense to everyone, that these are the two possibilities provided we are taking this as the state? Now this is a non-trivial state, of course, for now, because I think unless you see this once, it's not directly simple to come up with this particular state in a strings problem. But if you once now you know that, okay, in strings problem we generally see states in this form, so now we can think about this particular state whenever a string problem comes up in DP, right? Now once we have this particular state, we have two types of transition. One is like when we don't match and append it to the answer, we can either ignore the first character or the second character, like first character of the first string, or the last character of the first string and the last character of the second string. And the other cases, if they match, we can also do is we can append the last character as a last character of the answer, and then build the other part recursively from this particular part, right? So if we think about the length of the DP, that is going to form a recurrence relation, that DP of I comma j, okay, is equal to, let's say, either max of DP of I minus 1 comma j, just a second. Am I audible right now? Can I one of you quickly confirm? Okay, thanks. So this would be max of either DP of I minus 1 comma j, that I minus 1 comma j means that we ignored this particular character, right? And this is I and this is j. Okay, I in the first string, j in the second string. So we ignored this one. This particular possibility is there. After removing the large character, what is the maximum length we can create? Okay, that's this DP returning, right? The length LCS, so longest common subsequence of this particular part. That's what our DP is returning. And this particular part will return DP of I comma j minus 1, right? This is the two possibility. This is of course a possibility every time. Okay, this is always there. Okay. Also, there is one more possibility that we might have DP of I minus 1 comma j minus 1 plus 1. This is going to be the length of this particular part, like this particular part, plus 1, because that's going to append at the end. If and only if so this gets considered only if S1 of I is equal to S2 of j. Make sense? Out of these three things, whatever is maximum, you take that, and that is going to be your DP of this I comma j state, right? Because these are the only three things that can happen with the last character, and based on this last character, we are trying to define the recurrence. Of course, you can also flip the states, and you can say that okay, the states would say something like S1 of I to n and S2 J to M, something like this. This is also a possible states. So in a lot of DP problems, you can think of the problem from front to back or back to front, but this it's okay. You can, it's just about thinking in one of the directions and then building the recursion state. Okay. Yeah, that's all. That's more. That's going to be always better, but still, it doesn't take a harm to add one or two transition, like one or two transitions. Okay, so it's always going to be better, because if we are ignoring one character, like, so the idea is, if like let's say we have some I comma j, okay, this is I comma j, so we are going over here with 0 profit and 0 profit. Instead we can go to this particular point at 1 profit, right? So even after this, if we have to do 1 profit, we will always have to move in this direction, that I minus 1 j minus 1. So we are going to reach some point which is like less than I minus something less than this particular point, like which is reachable from this in 0 cost for sure. So that's why this is always better than this particular part if this is true. So you can, if this is true, then you can always compute this, or else max of these and these. But it's okay even if you take max of these three, because having one or two more transition does not help, does not like increase your cost much, right? So in some problems, you don't want to go about and think whether it will be always be optimal or not. So instead, use the way that is most safe, that will work every time. Is this state and idea clear, that what we are trying to store, that in such kind of string DPs, what we keep is this S of 0 to I and 0 to j, and based on that we create. Of course, there are base cases that I have not written right now. This base cases would be something like when one of the string gets empty, right? When one of the strings get empty, that means like you have to by default fill the values of S of like sorry DP of 0 comma x, sorry, just recurrence, and DP of x comma 0. Okay, these all values would not follow this particular recurrence, and this you have to calculate manually, because but that's pretty simple, because if it is same as this, then it's 1 or it's 0, same as this. and 0 comma 0 is if it's same, like for any x, if it is same as whatever at s1 of 0, then it's 1 or it's 0, similar for this. Okay, so these values you can calculate directly, and then as a base case, and then this particular recurrence that we talked about can be calculated, right? Now what would be the complexity for this recurrence? Using the technique that we discussed in the last session, that the time complexity of any DP solution is going to be the number of states multiplied by average number of transitions. So what is going to be the total time complexity? Yeah, so let's say this is going of length n and the other one is of length m, like s1 is of length n and s2 is of length m. Okay, so in that case it's going to be there is n into m, like this can take 0 to n minus 1 values, this can take 0 to m minus 1 values. Okay, so this is there is n into m number of states, and from every state you are doing order 1 transition, like there are 2 or 3 transitions, right? So it's order 1. So this is going to be order n into m. Is this clear to everyone? Can I have a plus point? This is clear, because this is an important DP. Okay, great. Okay, so now let's talk about the next problem then. How to find the LCS string. Okay, let's talk about that as well if you want to. So let me give you an idea then how to find the answer. Okay, so when you are calculating some DP of I comma j, right, in that case it will either take from I minus 1 comma j minus 1, right? I minus 1 comma j, it can either take from I minus 1 comma j, sorry, I comma j minus 1, okay, the max of these two, or it can go to I minus 1 comma j minus 1, right? This is the 3 possibilities. Okay. So for this particular position, keep that from, so for this particular value you are taking max of these three, so like whatever the answer for this, plus 1 plus 0 plus 0. Okay, so whichever of these is giving you a max length, okay, whichever of these three is going to give you a max length over here, that is the smaller subproblem from which you should get the rest of the answers, right? Like let's say this is possible, so we know that from this particular state we are going to get the rest of the answer, right? So remember, how did we go to this particular state? We said that the last character is going to append to the answer, and this all will create another subsequence, right? So that's what we are going to do over here as well, that if this is the one that is giving us the maximum value that we are saving over here, then what we will do is we will append the last character to the, like we know the last character now, and we have to calculate the answer from this particular state. Now what is the answer for this particular state? So recursively build the answer for this particular state and append whatever the like character that is at like this, at I comma j. So this is only possible when s1 of I is equal to s2 of j. Okay, makes sense? So in that case, find out the, like let's say we have some function which finds answer, find answer. Okay, so of course don't create it as a function which returns string and other things. Instead, once you build this array, once you're building this array, also store, like we know that we have a recursive function and that also builds an array, right? Which is some sort of memo table. So also create a instead of apart from memo table, create another array called, let's say something called back pointer. Okay, which will give you that, okay, given this particular state, from which state I'm getting like the rest of the answer, right? So let's say back pointer of I comma j is the pair I minus 1 comma j minus 1. So you straight away know that, okay, I need to append something like, or you can even store it in triples. Let's say you can store something like, this, that character a, like let's assume that at the s1 of I was equal to a, and they were same as well. So in that case, you can save at this particular state this triplet, okay? And then from this, you know that you are going to append a at the end, and you are going to form the answer, rest of the answer from this state. So just iteratively go to that, build it, and then finally append a in that answer, right? So in this way, you can create. So basically, at this particular state, how are you getting max? Like which of the values is finally reaching to this particular value? That is what is going to dictate what is the subsequence that you are forming. So in that case, you have to create this kind of back pointers, right? In case like you are coming from this, you have to create back, like you have to, this is just a 2D array, okay? This is not some recursive function. So back pointer of something called I and j is equal to, let's say, I comma j minus 1, and this is going to be some empty character, okay? So in that case, you know that you don't need to append anything, okay? So based on this, you can create the whole string if you want. And in fact, if you see the external problems, so some of the questions were added to the DP section, more will be added soon, but you are requested to complete those first. In that as well, if you see the F problem, the LCS problem, there is LCS is present in that. So in that, you have to print the string as well. So this kind of back pointers help you in some string. Of course, the general idea is, this is just the way I implement it, but the general idea is you should try to think about how do you like keep the sequence which is creating the maximum value at every index, right, at the end index. So based on that, you can implement it anyway. So this is something you should try on your own first, like how do you implement it, and after that you can of course look at any other implementation available, right? So this is just how to calculate number of common subsequence length k. How to calculate the number of common subsequences of length k. So we can count that, but it's not really related to this particular problem. Like that's a different DP. So that's I'm not discussing that particular problem right now, but I hope this particular back pointer idea, that how we are building the string, is clear, right? Okay, then let's move to the next problem. So you have, let's say, some sort of DQ. So there is a DQ, and in that DQ there are elements, okay? And there are two players, player 1 and player 2, okay? Now both the players alternate their moves. Let's say player 1 is you and player 2 is me. So first you go ahead and you take one of the values from either the front or the end, okay? You go ahead and take the front or the end, okay? Let's say you go ahead and take 4, so you get a +4 score, okay? And this gets removed, okay? Now it's my move, so I go ahead and I, let's say, take 3, so I get a +3 and 3 gets removed, okay? Then you can go and take either 2 or 1, because like either the first element or the last element of the DQ. So let's say you take 2, you get a +2. I go ahead, I take 1, I get a +1, right? So in that case, my total score would be equal to, so your total score would be equal to 6 and my total score would be equal to 4, right? These are the only, like, this is one particular sequence that we can follow, and I think it's optimal for both of us, so that's what we will follow. So in this particular game, you can assume that the player 2 is always playing optimally, okay? So you will get a score of 6 by taking 4 and 2. I will get a score of 4, right? So player 1's goal is to increase his score, player 2 goal is to increase his score. So in total, finally we want to find, let's say, what is the score of player 1 minus score of player 2. This is a metric that we are interested in. Now note that if player 1 moves, he will try to increase this. If player 2 moves, he will try to decrease this, right? Make sense? So what is the, you are the player 1 and player 2 is like some computer or AI trained, which is perfect. Okay, once you give him the chance, he will always play optimally. So what is your strategy to increase, like you are player one, so what's your strategy to increase this score, like this particular score as much as possible? And what, so you need to find that particular score. Make sense? So find out the score, that like maximum difference of score that you can create if you play optimally. Think about this problem for me. Constraints. So let's say there are only two elements that you need to consider about, n, and n is less than equal to 10 to the power, or let's say 5,000, something like this. And AI is less than equal to 10 to the power 9. Think about this for a minute. So think about it for a minute and then maybe write the answer in the chat. Like, don't try to write directly. Take some time. Think about this particular problem, that how do you decide on which to take. So Balakrishna is saying that at each time we can go for the one max, like both the optimal strategy is to go for the max out of the two, and we will add it to the result. Like we calculate the player one and player two scores and calculate the score, right? So let's talk about this particular instance. Let's say you have 4, 10, 1, 3. So this is the DQ state. Okay. Now, if you play greedily, like if you take the max every time, so P1 will take this, okay, and then P2 will take this, and then P1 will take this, and P2 will take this, okay. So P2 is equal to 11, and P1 is equal to 7, right? If we again think about this particular problem, the actual optimal strategy would be to take 3. Okay. So if you are doing recursion, then that's okay. But how, like, if you're doing recursion, then like what is the parameter that, like, so if you're saying recursion, then that's more or less like something sort of DP. So what is the state that you're talking about? So if the greedy directly don't work, because if you take 3 over here, then your opponent has to take either like 1 or 4. Whichever he takes, you will get 10. So he will take 4 and you will get 10. And
Can we take it as a array? I mean, 3, 1, 10, 4 are stored in an array, and then we will pass the states I and j, like initially it would be 0 to n minus 1, and on recursion calls we can take it as max of 3, then minus 1 to n minus 1, and then 4 comma 0 to n minus 2.
Yep, that will work. So there are a lot of ways to implement this. Of course, we will take this in an array, and after that, what we will do is we will try to create a DP. So DP would be something like DP of L to R, which is so like let's take the subsequence L to R. Okay, some length L, some subsequence L to R in the original string. What is the maximum score that, like, let's say you want to find out what is the, just a second, what is the maximum score that you can create, maximum difference of score that the first player can create. Let's say, let's save that. What is the maximum difference of score, like P1 minus P2, right? That's what we are interested in. We don't even want like P1 score. Like, of course, if we know the P1 score, we can find out P2 score. But let's say we want to find the max difference of score between two players. Okay? That the first, like, whose move it is will like get. Okay? The max difference of score that can be created. Okay. This is what we are trying to store in the DP. So that's why we are not storing the player number, like whether it's 0 or 1, because let's say whoever moves first, because in that way, in that sense, we will call the recurrence. Okay. So let's say we keep it in this particular fashion. Okay. Now, how do we find out this particular recurrence? Now, this is straightforward to think that from we are starting with the state 0 comma n minus 1, right? That we have the full array. Now we have the choice that we either remove this or remove this, right? So from DP of 0 comma n, so from some L to R, okay, some L to R, either we remove the last rth one or the lth one, right? So this is going to be equal to max of two choices. Either you take DP of, so either you will take, like, whoever first move it is, he will take, sorry, this should be equal to A of, like, ARR of, let's call this array ARR. Okay. So ARR of L minus DP of I plus 1 comma j. I'm going to explain why I suddenly wrote minus and everything. Just a second. Or else this is going to be equal to ARR of R minus DP of I comma j minus 1. Now, how did I come up to this particular expression? Now, what is this particular expression that I'm writing over here? Whosoever move it is from this for the rest of the string, like if this is the whole string, I took the first one. Whosoever move it is the next move. What is the best difference he can create for himself, right? So after this move, let's say at this particular move, it was P1's move, right? So we have to find P1 score minus P2 score, okay? So what we do is we do a plus ARR of L, because P1 takes ARR of L, right? So plus ARR of L, okay? And then for this particular part, it's P2's move first, right? So the optimal value over here would be P2 score, maximum value of P2 score minus P1 score, right? Maximum value of this. So of course, at this particular instance, P2 will also play optimally, because if you are playing optimal, if this is the optimal strategy, if you are following the optimal strategy, P2 will also follow the optimal strategy, right? So he will take the same recurrence. So at this particular state, he will know that, okay, I need to play whatever the answer for DP of I plus 1 comma j is, right? And that will be his P2 score minus P1 score, right? So this particular metric over here is nothing but P2 score after this minus P1 score. Okay. So the current this particular difference that we can have to create is going to be equal to minus P2 score minus P1 score, because if we put this particular value over there, we are going to get whatever P1 score after this move was plus ARR of L, like this particular move, minus P2 score, right? And this is what we were interested in, right? That, okay, this I will take, and then whatever my opponent's optimal score is and my optimal score is, this is the expression that we were interested in. And in fact, if we write this kind of differences in DP state, it becomes much more trivial to write this subtraction and quickly do this. if you remember, this is something we have also seen in the problem in brute force, where we had the move, like we had to move on the grid and who would move, who would win, if you remember that. We kept a similar kind of rooms like restrict the rooms game that we had from Kickstart. So in that as well, we tried to keep this difference so that we could subtract this very easily and get this. So keep this idea in mind whenever you are writing states. So we could have kept it in that fashion as well, that whoever move it is, what's his score. But that would have like needed some of the range to be kept as well. Of course we could do that as well, but it's always better to like keep minimal dependencies, right? Is this clear to everyone? So this is very straightforward DP of this, and like I think there is no reason to like think about anything in this particular thing. Like now after this array is saved and this L2R is there, now from this you just need to find the max of two particular recurrence. Now these are two recurrence, simple recurrences. If the range becomes empty, then you of course know its answer is 0. So just simply build the recurrence and memoize it, right? Is this clear? Yeah. Okay. So I think this is clear to most of you. Is it clear to everyone? I think some of you not even responding most of the places. Okay, fine. So let's then move to the next problem. Okay, this is fairly straightforward to implement as well. I think there is no need to implement. Let's move to the next one. Next one is an interesting one. Okay. If you want to return the individual scores, is there a way we do it? Yeah, even with this particular version, you can find out their individual scores, right? Because in this particular game, you know that finally DQ will empty. So P1 score plus P2 score is equal to sum of array, and P1 score minus P2 score is equal to your optimal value that you get. So from this, you can find out their individual scores, right, from these two questions. Okay, so now let's talk about another problem. So you are given, like there are n players, okay, there are n players, and each player, like each of the ith player, let's say, has two attributes, x of I and y of I. Okay, there are two attributes given to each of them. Make sense? Now you can, now for every player you will have to make a choice that either you don't take him, you take him, like sorry, don't take, okay, you take his x at x's act, like the player you take, its x attribute is going to use, okay, and the player you take, it's his y attribute is going to be used, okay. There are only three choices for every player, like either you don't take him, you take him for his x attribute, or you take him for his y attribute, okay. These are the only choices that you have, okay. Now you are given a input a as well, like some constant a, and you have to take exactly a players of for attribute a, and you're also given an input b, like these are not characters, these are string, these are numbers, okay, like you will be given 2 and 3, let's say a equal to 2 and b equal to 3, let's say this. So this will mean that you will have to take out of n players exactly a number of players which is taken for attribute x, and exactly b number of players who are taken for their y attribute, okay. And like whichever players you take, like if you take that player for their x attribute, then we have a metric which is like score, and it gets added with whichever score you take, whichever part you take it for. So either x of I or whichever, like y of j, whichever, whatever you take it for, like whatever you build the team with a number of x attributes and y number of b attributes, all these a players X attributes get added and all these B players Y attribute get added, and finding that total sum is what you need. That's the score of your team, and you want to maximize this particular score. So how do you optimally make your team? Is the question clear to everyone that out of n players, you have to take A players for their X attributes, B players for their Y attributes, and the sum of their corresponding X or Y, whichever they are chosen for, their summation is going to form the team score, and you have to maximize the team score. Okay, and you are given the constraint that of course A plus B is less than equal to n. Like, of course this has to hold, right? Now, what is the maximum score that you can create? Xi's and Yi's are given to you as inputs. They are large. Okay. So no constraints on this problem. Think about how do you just solve this particular problem. So think about it for a minute. No answers directly. Just think about first. We have to maximize this score, that whatever team you are building, the sum of their corresponding Xi's and Yi's for whichever they are taken for, that player is taken for, their Xi's and Yi's will get added, and a score is formed for the team, which is sum of everything, those A players and B players. You have to maximize that. Is the question clear to everyone? Okay. Just think about it for 1 or 2 minutes. This is a good question. So you can think about this. So there are A plus B players in total in the team, right? A of them will get their X scores added, and B of them will get their Y scores added, and add all of them together, and then that's the score that you're trying to maximize. Okay. So for all those B's, you take Y's, Yi's. For all those A's, you take Xi's and add all of them together. That's your score. Yes, Vishesh, we can do this better than NQ. But like, of course, NQ is one step, but we can do this better than NQ. Okay, so now any ideas on what do we keep in the recursion parameters or states?
Hello.
Yeah.
It's big. So we will sort with respect to X and then with respect to Y and maintain both the arrays. And if like for the optimal solution, So if we now we want to take the maximum one. So the maximum one can be like same. So the maximum one in the with respect to x and with respect to y may have the same index. So we can
Yeah.
take only once.
Yeah. So how are you
So
maintaining?
so like we will sort, we will store also the index also. So it's something like the LCS problem. I'm solving something like the LCS problem. So if they are different, we will take both of them, and then the solution will be like for the rest of the
Okay,
indices.
okay. No, no. I think this will not work because like when you are saying that I'm sorting it by greedy and they're both same, it might be optimal to. You will have to take a y. Okay, let me explain this over here. Let's say there is. Okay, so this is x's sorted order and this is y's sorted order. Let me just give me once. Even to think about an anti-test case. So I'm taking the indexes over in this lower part. In this particular state, then. So in this particular state, which one will you take? Like you will start from this. Let's say if you sort it, you will get these two elements. So you will take both of them. That means you will not be able to take this, right? So based on that, I will like keep this 8 or 9 or this or 9 or 8, whichever is. Like these are y values and x values, and I'm keeping the index as well. Now, like if you take both of them because they are like not same and they are quite large, so in that case, I will make this one this one 8 and this one 9, so that you cannot take you have to take you will take 8 instead. You could have taken these three, like these are 4, let's say, and on the other side I will flip this. So if you just take these two cases, I think one of your like your idea will fail on one of them, because
Okay.
okay. So yeah, LCS will not work. What I think in NQ, what Bala was saying, I think Vijesh also thought about the same state, I guess, because that's the only NQ that also comes up, that DP of index comma number of chosen X attributes, number of chosen Y attributes. Yeah, yeah. This is what almost it looks like. So we are currently, let's talk about what the state is saying. So let's say we have the array, okay, and this has a partition, and this is the xi values, this is the yi values, right? Makes sense. So from this particular state, we keep dp of like I comma a comma b, which means you have taken up to ith index. Okay, you're considering the prefix 0 to I, like you're considering the prefix 0 to I. Okay, and in that particular range, you're saying that okay, I need to take a number of x attributes 1 and b number of y attribute 1. Okay, so these a and b are not the, like we will call it with the actual parameter, but these are like now the parameter of recursion, not the actual a and b input. And in general, let's keep this as capital A and capital. So from first I elements, I need a number of x contributing players and y number of y contributing players. Now, as soon as you think about this particular state, it is quite straightforward to think about the transition, that for a dp of I comma a comma b, there are three moves that possibly can happen, that you can possibly do. You will take max of across all. Okay, max across all. Now the first is either you don't take anyone, so you go to I minus 1. You don't take the ith player, and you fulfill your requirement from I minus 1 players. Okay, or you take the take the ith player for its x attribute. In that case, you need a minus 1 more attributes from the previous I minus 1 elements and b over here plus x of I, provided a is greater than 0. Okay, and the other is dp of I minus 1 comma a comma b minus 1. You take it for his y attribute, and provided they have b is greater than 0, right? And you take max of all these three values. Is this state clear to everyone? Because this is more or less what we need to keep in this, right? We need to know the number of people we have taken till now. So in general sense, when we are talking about DP, whenever you need to think about this kind of recursions, that how to design this recursion, think about like DP of, this should be your first thing, that DP of I is most common, that which up to which index we have processed. Okay, after that, what is the additional constraints that we want to put on the data items that we are picking up? Okay, keep those constraints count or sum or something like that in the, no, a plus b is less than equal to n. It's not given equal to n. A plus b, I wrote less than equal to n, right? This is less than equal to n. So if a plus b, yeah, if a plus b is, okay, let's talk about that as well. Okay, so first let me complete this one. That in general, when you want to find like what is the state, so think about the constraints or sum or let's say parity or whatever you need to maintain, the constraints of the question that you have to maintain for the solution space, that you try to maintain somehow through the states. Okay, so these things you keep in the state, that you have to take at most a only, so a can only decrease. You start with, so we will call it with dp of let's say n minus 1 comma let's say a, the input a and input b, and this will give us the full answer because this will calculate whatever is needed, right? So these constraints are kept over in the states, and calculation, max, min, count, sum, these things are done in the answer, like they are getting added and everything. Okay, so this is how you generally form the recursion states. Okay, now let's talk about the time complexity of this. I think most of you have already suggested what time complexity should be, and it's straightforward as well, because we have taken a lot of such discussion till now. So in general, this can be a can be up to n itself, b can be up to n itself, I can be up to n, I is up, of course, up to n. So this can be this can have n cube states, and for every state you have order 1 transitions, right? Not exactly, like more or less in the correct direction, but not exactly. Yeah, so let me complete this first. So the total complexity would be order n cube, right? So Vijay is saying something like, we convert this to knapsack with A available spaces, and for the rest of the things we will maintain y. So for the rest of the things you will have to maintain top b of y. How do you define rest of the things top y? Because it's not going to be continuous array, right? Makes sense? That's going to be difficult. But the direction is almost correct. Okay. Let's talk about what if. So let's now talk about the case where I think, yeah, if a plus b, yeah, let's talk about a plus b. What do we do in that case? A plus b is equal to n, I mean to say. Okay, so in that case, like we can straight away decrease this dp to, like this dp was order n cube, we can straight away decrease it to order n square by using something called state space reduction. Okay, let me explain what this is, just a fancy term. So this basically means that we know we are keeping, so we are convinced that okay, dp of I comma a comma b will work for sure, right? Now we know that a plus b is equal to I at all possible steps, because we have to take all elements, right? So whichever elements we have to take, that is going to follow this particular constraint, right? So we know that, let's say b is equal to I minus a, right? Make sense? So why to keep b in the recursion parameter? What we can do is we can change the code a bit, and like we were writing something like this, right? dp of recurrence integer I, integer a, integer b, and then we were writing code, right? This is what we were doing basically when you're talking about recursion, right? Instead, what I do is I just drop this parameter over here, and I just get integer b equal to I minus a. This is also correct because this constraint is always followed in the problem, right? Make sense? So if this is also always following, so why to keep this in the state rather than that just like get that value inside it, right? So that you don't have to store it again and again. So from this, now we can say that, okay, there was total n cube number of states, but now there are only order n square number of states, because we know that for a unique a, there is a unique, like for a unique pair of I comma a, there is a unique b. So the rest of b's are not getting used. So why to keep that in state? Just remove it into the code, like derive it from these parameters, and like now your state is just order n square, and from that, like transition still remains the same, exact same, nothing, no difference. Okay, and we can get the answer in order n square, right? Is this clear to everyone? That this particular constraint will always hold if a plus b is equal to n, because we are considering the first I elements, and across the whole array we have to take all elements. So across the first I elements as well, we have to take all elements, right? So this has to hold true. Make sense? So from total whole array, we just like quickly reduce this particular from this 3 states, we reduce this b state, right? We remove this from the state, and this got to n square. So if you like quickly see what is the reduction that we have been doing till now. So initially our code was order like 3 to the power n, because for every element we had 3 choices, right? And then we memoized it. Like if you just code this without memoization, if you code this recurrence without memoization, that without storing it in some array, in 2D, in 3D array, in this particular problem, this is going to be a 3 to the power n recursion, because for every element you have 3 choices. Don't take it for x, take it for y, right? 3 choices. So this is going to be 3 to the power n. As soon as you apply dp, this becomes order n cube, right? This is the power of dp, that this many states are getting recomputed again and again. Okay, and now after this we say that, okay, if a plus b is equal to n, then we could reduce it to order n square, right? But there was this big if, right? Can we reduce it without even like any extra condition? Like let's say still a plus b is less than equal to n. Can we reduce it to something like n square using the same kind of idea that we discussed just now? Like, so that at every point we know that some part will always, like some particular part will always be taken, or how do we, yeah.
Right. So even if a plus b is equal, no, less than n, can we not say that if we solve the thing for equal to n, and then choose the a x's that we get, and then out of the whole n minus a y's, we choose the top b, then that will be the same answer as if a plus b was less than n?
No, that will not work. Why? Because you don't know in which order they should get removed. Like there are index, like you are saying that you will first remove all n minus a, like whichever a's were extras, x were extras, and whichever y were extra. But like who knows that, like the elements that got removed there might have been some choice, like you removed x altogether, right? There might have been a choice where y got removed, and like x could have got some other element instead of what you have already taken, and so on. So it's not directly clear like which all should we get. Like out of all those a plus some, let's say we took some delta amount more which was not needed. So out of this a plus delta, which of the delta should be removed? Like should be, so you are saying that we should remove the smallest x values, right, which we took. That's what we are suggesting, right? So how do we know the what, like this dp state does not compute the smallest a values that you took, right? We don't know what is the smallest x values we took, smallest extra values we took. we can keep track, okay, we can keep track of how many A's we have taken, but we cannot keep track of how many, like what are the sum of the smallest values that we have taken, right? That is, for that we have to introduce maybe one more state into the recursion, and that is not going to be feasible in this problem, okay? Because that's not feasible. Like you're, then if you just build one solution, like we are storing the number, right? We are storing the answer over here. So there might be multiple possible configuration that result in the same answer. Now some configuration might not have, like some configuration, two configuration can have the same answer, right? Same value in terms of like xi plus yi. But if you, let's say, generate one of them, like if you just build one of them and then brute, like if you just greedily remove, do some operation on that, that is not going to be correct, because there might have been some other way to create the same value, and that particular way might have given you some other better optimal value, right? So that's why in such cases, like it's never like, it's in generally in DP, when you want to optimize, you generally don't see into like things like, okay, I will first solve the question, get the answer, and then do a pruning on answer. That's not going to work in most of the DP problems, okay? So like whenever you need to prune, don't like go into this direction, that I will first solve, get the answer, and then for that particular answer I will just prune it and improve it, because there might have been some other answers which gave me which might have given me the same value. So what about those? Those might have got pruned better. Keep each player as x minus y profit. Yeah, that's perfectly possible. A plus b plus c is equal to a plus b plus c equal to n is a good idea, but that is again going to introduce like some extra state. Like it's not going to reduce, it's not going to reduce state, right? When you're like this, it's not going to reduce the state. Like of course that's one way to think about it, but that's not going to just like remove n cube from it, right? So let me like directly go into the solution. I think most of you are not going in the correct direction. What if we sort it by some particular value? Like what if we sort it by some particular value to ensure that this particular condition holds every time, like for some prefix that it always holds, okay? So let me explain how are we doing this. This is a bit non-trivial, okay? So let's say we sort the input, like we sort the given input in by their y values, okay? We sort the input by their y values, okay? So now we have a sorted, now we have a sequence, and the y values are like decreasingly sorted, okay? So this yi is always greater than this yi plus 1 and so on, right? Yi's are sorted decrease in a decreasing order, okay? And xi's are in random order, like we don't know about x1 x2, we don't know anything about x1 x2, right? But y1 are decreasing sorted. This we can do, right? I hope all of you agree with this, right? That we can sort the input itself, right? That we can sort it and in decreasing order of y, okay? Now once we sort this particular sequence, note that what has happened in the problem, that let's say there is some xi and yi, okay, and there is next xi plus 1 and yi plus 1, okay, and till now you have taken some elements and some other things that happened, and then you want to consider this particular element, okay? Now let's say you know that, okay, you need to take a more elements and b more elements, right? Let's talk about, like let's talk about this much leftover state, okay, this much left state. Let's say out of, we were just changing the, we are transposing the things a bit. We are saying that out of the last k elements, we will choose which one to take, okay? Which I mean to say which all elements to take, which all. So initially we were keeping dp as dp of i comma j, I comma a comma b, which was like out of the first I elements, what is the best way to take a x and y b and b y's, right? A x and b y's. Now we are saying that in the subarray I to n, Okay, starting from I till n, what is the best way to take a number of xi's and b number of yi's? Okay, make sense? Yeah, let me explain that. Yeah. So now note that once we do this sorting, right, what I claim is, like when we have to, like, let's say from this particular state, we have to like take, let's say, uh, a number of x and b number of b. So for the first element, we have three choices, right? Either you take it for xi, either you take it for yi, or you don't take it. Okay. Now, due to this sorting, there is a nice property that comes up, that it is never going to be optimal to not take it unless b is equal to 0. Okay. It's never optimal to not take it unless b is equal to 0. Why? Because let's say b, let's take b equal to 1 only. Like you need just one more y out of everything left from this ith index to next n index, right? Let's say you have taken some elements, you will take some elements over here, and then from I to n you need a xi's and b yi. Okay, so now at the ith index, if you choose xi, then well and good. From the rest of the things, like from over this part, you need from I plus 1 you need a minus 1 comma same b, right? Now if you don't take yi from over here, you will take some element later on which has some xj and yj, right? So you will take its y, because this has to get satisfied, right? This has to get satisfied at some point of time in the whole array, right? B has to get at least one element. But if you are taking this element and you are completely not taking this element, like if you are not taking it for xi and you are not taking it for yi, that means you are not taking this element, and you are taking this element for y's. So why not take this, because this has better y than this y, right? Because that's why we have sorted it. Make sense? If you are dropping this particular value, how do you compare 3 4 and 4 3 in final answer? So we are getting, no, we don't, there is no difference between them, right? So xi's we add, yi's and we add, and then add both of them as well, like total of x plus y's. Okay, so the main idea is, of course we will do the same dp on x, that okay, dp of I, that first I elements. So in the last I elements, let's say how many a's do we need, but we don't keep b, because we know that, like let's say in this particular range, okay, I need to find that, okay, from this I to n, I have to get a number of, sorry, I'm just renaming this a bit, just to, okay, let's keep it here. I will call the input, that will x plus y. So how is this going to help us? Like how are we like doing it on a and b? Like how is that going to constrain a and b? So after that we'll have to decide which to take, right? No, that's not going to be optimal at all places. That's not going to be optimal at all places. Like even after sorting, like the first a plus b element might not be necessarily optimal, because there might be multiple values which has same x plus y. So how do you decide on which one to take and which one to not take? Okay, so as I said, never do first some optimal approach, like first solve for one answer and then use that to prune. Like that is never going to work. Okay, either you do it fully on input, you can reorder the input, that's okay, but you don't take one solution and then prune it, right? You have to consider all solution spaces. Okay, so let's come back to this. We made a very important claim over here, that once we sort this, and in this array, if you want one yi, and if we are not taking the first element for its xi, then we will take it for sure for yi, because anyways after like in the later part, if we take something for yi, that yj, sorry, for some yj, that yj is less than this yi, so why not take it over here itself, right? Because we are not taking it for xi, and if we are taking it for xi, then well and good, let's go to the next element, right? So once we sort it for yi, we now know that out of all these elements, we will take like yi's from whichever element we have not taken till now, if we need yi, or else we will take xi, right? So we are not pruning it to the first a plus b element. Note this part. We are not pruning it. We are just saying that for the first few elements which we are not taking for x, for first b element which we are not taking for x, we will take them for y. But after that, we leave the choice for x, that x might not take some next element over here, and then it might take something over here. It might be possible, right? Because x is not sorted. Make sense? So this particular reduction allows us to calculate the dp using this particular relation, that dp of I comma a, that okay, what is, you need I number of, from I to n, you need a number of x's. So you need to find out, so from this we need to derive what is the number of, what is the value of b. Okay, can someone quickly find out the value of b? Like, can you think about how do we retrieve the value of b? Because unless we do that, that's not going to hold true, right? Make sense? Like, are you getting with the point? No, it's not I minus a, it's not I minus a. Okay, let me explain. Yeah, if I is less than a plus b, then no, that's not true. So okay, let me remove some confusion. There is a capital A and B that are given as the input, that is equal to the actual number of A's you need, the number of B's you need, and this A and B are like, from this part, how many A's do you need? Okay, so let me try to derive the expression. So let's say this is the array, and sorry, okay, this is the array, and from this you need to calculate, let's say you need to take a number of elements, right? So let's say this is the index. Okay, so how many elements have we processed till now? Which is that will be same as index, right? I guess, yeah. So the number of elements that we have processed till now is going to be equal to I, okay, minus the, we need out of the total a elements from over here, right? So a minus a elements has been taken from over here, right? A minus a elements has been taken from over here. Okay, now this is going to be, now this is going to be the number of b's taken from this particular space, right? This is going to be equal to the number of b's taken from this particular space. Now total number of elements taken minus the total number of a's taken. Of course there is a condition that b should not get to like more than the, like less than the number of b's that is available. Okay, so that will handle separately, but let me just quickly explain over here. Like, this is the number of this is the number of a's in this range. So the number of a's that you have taken in this particular part is a minus a, and total number of elements that you might have taken at max is I. So this is the maximum number of b's that you need from this particular range. Okay, and that you can say is nothing but b minus b. Okay, because if you need, let's say, b number of elements from over here, then you should have taken b minus b number of elements from this particular part, right? And from this we can find out the value of b. Okay, we need the value b, right? That's the target, that how many b's do we need in this. B, capital B minus b is the number of b's you take from this particular part. Okay, so this type of relation you write, and then you can find out the value of b, okay, from this particular expression. Of course there are some parts that you have to take care of. Yeah, that minimum, you have to take minimum with some things, that okay, this is the number of, so this is the number of I mean to say, this is the number of b's you can take from this particular part, right? So this is the number of b's you need from this particular part. Of course, if this is going, if this is negative, then it's not a valid state. Okay, so we don't even calculate that. Apart from that, this is always going to hold true. And in case this b becomes more than, like, if this is going to, if from this expression, if you calculate and b becomes more than b, then you take a min with b, right? Like you make it b. Make sense? Like, if this is negative, then this will become more than b, right? So you make it b because you don't need more than b. So this is how you write the expressions, like based on the DP state that we decided, you write the expressions for the left hand side and whatever you have done till now. And based on that, you write this expression and find out the value out of it, right? Is this expression making sense? How do we get this particular expression? Right. This is again a state space reduction itself, just a bit more complex, like just a bit more complex expression. This is nothing but a simple linear equation, right? Like this is a linear, like you can just transpose and calculate the value. Okay. So from this state, from this particular equation, we can say that, okay, even for this particular state, we don't need to keep B. So we can drop, so we can calculate B from this expression. So drop B in this DP and calculate it with just A. Okay. How we are getting this? When you are talking about how are we getting this particular expression over here? Yep. Okay. Let's quickly revisit that. So in this particular array, we know that we are at index I, and from this I to n minus 1, we have to find out a number of xi's contribution. Okay. So in total, we had to take a number of xi's contribution, and a of them are coming from this particular part. So how many have we taken till now? A minus A, right? This many we have taken till now. Okay. Now we claimed that if we are not taking some element from the prefix to A to xi's, then we are going to take those for bi's, right? So there are total I number of elements over here. If this is the index I, then if this is 0 index and this is index I, then there are I number of elements over here up till this point. Okay. So I minus A is going to be the number of elements that is free for B. Okay. And then yeah, it is finally B minus, yeah, this exact, that's correct, that's the correct expression. So you just need to manipulate it a bit. I'm not exactly sure what it will come out to be. It's going to be B, yeah, it's coming out to be B plus A minus B plus A minus A minus B, yeah, minus A minus, yeah, minus A minus, yeah, correct, that's correct, right? So this part is the free B's, and this is nothing but the, if you need B number of yi's from this, then the number of yi's taken over here would be B minus B, and this is the thing that we calculated just now. So this is going to be B minus B. Okay. And make sure that this does not go less than 0 and this does not go more than B. Like in that case, you just make it either 0 or B, like clip it downward or upward. Okay. That's the number of B's you need. Okay. So that we can derive, and we can again do the recursion. Is this part clear? Is it clear to everyone? So this is now, once we drop this state, now again we have the, like, so we are doing the same thing that we were doing earlier. Like we have DP of I comma A, and there is a B as well calculated. Okay. Now with these we have the, like the normal 3 transitions that we can do. Like either you take this, don't take this, or like you just consider 3 transition itself. That will also work, because anyways we are calculating B. So you keep the rest of the code same, just delete B and calculate B in over here. That's it. Just remove that state. Okay. But only one thing, that you have to sort it by Y. Okay. That's the only change that we did to make this observation possible. Okay. Fine. So this was a lengthy problem. This now finally reduced to order n squaring. So there is an order n log n to sort, but of course it's dominated by order n square, right? There is an n log n to sort, but that's not going to be relevant. Okay. So it's going to be order n square. Okay. That's one question. So this is something called sorting plus DP based problems. Like there is a class of this kind of problems where this is sorting plus DP, that you need to sort and then use DP on that. Okay. You will see that there are some problems as well in which you need to first sort it by some greedy condition, like exchange argument, which we have discussed, and then use a DP. That is also feasible state. Like that's also possible, but we will take up those questions later. Okay. Let's talk about one last style of problems today, which is game based DP. Okay. So we will take up a very standard game, something called subtraction game. Okay. So let me first of all tell you about what this game is. Okay, the game that we're talking about. So there are some conditions that these game need to follow for DP to hold. So we are of course talking about combinatorial games. Okay, and something called impartial games. Okay, so combinatorial games are something which gets to a result, and impartial means that both the players have like identical choices, like they don't have any difference. Okay, like it's just about the move, whose move it is. Rest everything, the rule is same for both the players, right? Those type of games are called impartial games. Okay? Now with these in setting, if the game does not like goes on for infinity, we can find out the value, like who is going to win or lose the game using DP. So let's talk about one particular example. That let's say there are like n stones on a deck, okay, n stones on a pile, and in one move you will be given k possible values, like let's say k1, k2, k3, k, sorry, let's call this m, km. Okay, km, like m different possible values, and k1, k2, k3, km. Now you start with n number of stones on the pile, and you can take out any number of stones which is equal to, like, which is out of this array. Like you can either take out k1 stones or k2 stones or k3 stones and so on, right? So with this possibilities available, find out who will win. Like let's say you are player 1, you play first, and then I'm player 2, I will play next after you. Like we will alternate the game, and then you need to tell me who will win the game. Okay, that's what we need to find out. Is the question making sense? That each player has a set of moves possible, that given this for and many these many like stones, you can take out these many stones out of the stack. Okay, like either k1, like let's take a concrete example with numbers. So let's say there are like 7 stones. Let's say there are 8 stones. Okay, and let's say we can take out either 1 stone or 2 stone or 3 stone out of the stack. Okay, make sense? So now you need to tell me who is going to win the game or who is going to lose the game. So let's say it's your move. Yeah, what is the criteria for winning? So whoever, okay, so what is winning? So basically in any game scenario, if the question, like if someone does not state anything, the standard is if you can't move, you lose. Okay, if you can't move, you lose. So this is the standard setting always, like for all games. Okay, so of course the number of stones is decreasing, so at some point of time you will not be able to make any move. Okay, note that this is going to be an input. In this case we are taking 3 numbers, but this is going to be a dynamic input like this array. Okay. Now if you can't move, you lose, and this is going to be like standard for any game. Now of course there are other rules as well, like you can play with the rule that who cannot move wins. That is something called Misery's game, like Misery, I don't know the exact pronunciation, this is some French word. Misery's game setting. Yeah. So there is a lot of different variations of Misery, and so there is a whole domain of game theory. We will not go into that now, but let's leave this apart. Let's think about how do we solve this particular part, right? If you just flip the rules, that if you cannot move, you win. That's called Misery's rule. If you sometime need it, you might Google it up, but let's leave that. Let's say if you want to find out who will win in this scenario, can you like find out that? Let's say I give you to play this particular. Okay. So what is going to be the answer for this game? Can someone quickly say? This I think you can even say without any computing anything. But that is something I'm not going to explain today. Like that's not the main agenda. But for this, I like in this particular game, I will like give you the move and I will ask you play the move. Can you play the good? Like can you play a move? Like what is your best move that you can play? I'm going to play player 2. Yeah, this in this game second player will win, and that's why I'm going to give you, yeah, that's why I'm going to give you to play first, because I'm going to win anyways in this one. If anybody wants to play, you can. So let me give you a strategy in this setting that will like help you think about it. So let's say whatever you move, let's say you move out any one out of these, I will always play 3 minus x. Sorry, 4 minus x, I mean to say. Whatever you play, I will play 4 minus x. Now, whatever you are thinking to play, just think about it and play with my, like, whatever you play, I will play 4 minus x. Just play with it and you will see that you will lose. It will be periodic, but we are not going to use that right now. No, this we have not even got to anything. Like I'm saying that, let's say if this is exact setting that you have 8 stones and we have 1, 2, 3. If you play whatever, so if you, let's say if you want to play 2, like let's say you are playing player 1. If you play 2, I will play 4 minus 2, that is 2. Okay. Then if you play 3, I will play 4 minus 3, which is equal to 1. And then it's your move. You cannot play because it's empty, so you lose, right? So this is my rule to win this game, in fact, and it will, in fact, this game is lost for player 1, whatever you do. We can repeat moves, not repeat like it's 4 minus x, but let's come back to the original problem. In the original problem, this might not be this might be 2, 3, 5. Okay. And in that case, rule like this does not work. Okay. So the version that I showed you was called continuous subtraction game, and in that particular game, you have a very nice rule that if you have like continuous moves like 1, 2, 3 up to some x, then if the number of stones over here, if n mod x plus 1 is equal to 0, then it's lost or else it's win. Okay. Like the previous version that we talked about where there were continuous move allowed, in that case just use this rule that if n mod x plus 1 is going to equal to be 0, then it's lost, like it's lost for you, because I will just flip your moves. I will always keep you at x plus 1, and or else I will win. First player wins. Okay. dp of I is not of dp of I minus ki kj for all j to n. If all of them, yeah. Yeah, this works more or less. Yeah. Either dp of n minus, now dp of, no, obviously this is not exactly working. Like this will not exactly work, like or will not work in this case. Let me explain how we, so this is what we are going to discuss today, like how do we design this dp for game. Okay. So this is something, a quick result. This is something we will take up in module 4. Something, there is a particular, so we will discuss game theory in some detail, not very big detail, because there is a complete chapter out on it, but like game theory is a small topic that is sometimes asked in competitive. So we will take up game theory in module 4, but not now. Okay. These type of result based games. Okay. Let's quickly talk about this particular version, that you have generalized n stone and there are m moves given to you, that is k1, k2, k3 and so on. Okay. So let's talk about in general, right? So what is good? Anyways, in this particular problem, there is only one possibility of state, that is dp of number of stones, right? Can there be any other state? No, right? Number of stones left. Okay. So basically we are saving dp of number of stones, which will give me is it winning for the first player, like whoever move it is. Okay. Okay. Right, this is what we are storing as dp. Is the dp state clear? Like what we are storing, that given this many stones, can the first player win? That's our dp. Okay. So 1 means if dp of, let's say in the previous state dp of n8 was 0, that means first player will lose. dp of 7 was 1. Okay, that means first player win. Is this dp state clear? Not, we are not talking about transition, just the state. Is this clear to everyone? Okay. Now let's talk about transitions. So we have some state in dp. Okay, some state. I'm not talking about I, just like in general game. Okay. Now from this state, if we move, let's say if we do a move let's say we reach S1, okay, we reach S2, let's say move 1, move 2, move 3, okay, S2, 3, and so on, right? Now, of course, since we are doing a move, as in we called about games that we will take up, in which like after a move, the game gets smaller, right? It does not increase, it cannot go to infinite number of moves, okay? So these are smaller states, so these can be computed first, okay? Now, from this particular state, if I do a move 1, let's say I go to state 1, okay? Now at this particular state, it is going to be player 2's move, okay? Let's say here it was player 1's move, here it will be player 2's move, okay? Now let's say this particular state is winning, okay? So this particular state is winning. Like from this state, there is an optimal strategy that will win for whoever move it is, okay? So should I go from this particular state to this state? No, right? Because this particular state is winning for my opponent. So at no cost, I would like to go to this particular state, right? So I would like to push my opponent to the state where it's losing, right? Let's say this state is losing, okay? So I will push, like if any one of the states is losing, I will push my opponent to that particular state and he will lose, right? Makes sense? So some state S is winning. If some followed state, like whichever state you can push your opponent to, is losing, okay? If there exists a state Si, okay, which is losing. Si means like states which I can go from S, okay? Let me like reiterate it. S is winning if some Si which I can go to, there exists a Si which is losing, okay? Or else S is losing if for all Si is winning, right? So basically, if you are at a particular state and no matter what you move, your opponent is going to win. So you are going to lose, right? Make sense? And if you are at a state and if you move something and you can push your opponent to a losing state, then he will lose, so you will win, right? So this is the complete basis for any DP based game that you will see, okay? And if you understand this concept, you should like, this is not even any concept, this is quite common sense, right? That at a particular move, if you can push your opponent to a losing state, he will push him, right? That's it. Okay. So that's all we will be following, okay? So if you think about it, what is it going to be in terms of DP recurrence? So DP of like whichever state you are at is going to be equal to, like let's say there is S1, S2, S3, okay? Let's say there are only 3. So what we will do is, like we will take up, we need to find, does there exist anyone which is losing? So if any one of them losing, if any one of them lose, then DP of S1 and DP of S2 and DP of S3, let me move a bit, DP of S3, out of these 3, at least if one of them is 0, then this is going to be winning, right? So we can say that, okay, this is going to be negation of this, okay? Make sense? So to whichever states you can go to, just take their ANDs, like if all of them are winning, then this is going to be losing, or else if one of them is losing, then this is going to be winning. Is this DP concept clear to everyone? Can I have a +1 if this is clear? Because this is important. This comes up quite often, like DP plus game setting. Okay. Okay. Now with this concept in mind, okay, yeah, these are impartial in terms of like rules. Of course, it's like pre-decided. Yeah. Okay, this is, let me just quickly confirm the term impartial games. No, impartial games can be pre-decided. Like even nim game is a impartial game and it's pre-decided. Like you don't need to know. So impartial game, like move does not depends on the position and it's like fixed. Okay. Okay. So this is the whole concept that you will use in this particular problem, and that from that this particular problem becomes fairly straightforward, right? How do we solve it? Like from every state I, like for this particular problem, this is nothing but like this is going to be very simple now. That dp of I is going to be like there are m states, right? K, all of them ki. So it's going to be not of like and of, or I will say, let's say product of, okay, product of. Anyways, if one of them is 0, it's going to be 0. Product of dp of I minus k of I, okay, if it's valid. Like if it's valid, then only we do this. Like if that move is valid, right? And if no move is there, like if no move, then by trivial laws, dp of I is 0, right? Because if there is no move, then dp of I is 0 because it's losing, right? So by default, dp of 0 is 0, and rest you can calculate using this rule, right? And from that you can get the answer. Now for every I, you need to traverse on all m. So what is the complexity for this? If dp of I means p1 is winning, then the recursion should be something else. Why? Because okay, this means, just a second, if this is winning, if all of them are winning, then this is going to be 1, so this is going to be losing. No, I'm not really sure. Why is this wrong? Like if p1 is winning, then recurrence should be different. Why? Like I'm going to say this is 1 minus this.
So you said that we will go to one of these states. So if one of these states has 0, then the P1 will win. It
Yes.
means
So that will happen over here, right? If one of them is 0, then the product will become 0. So this is going to be 1.
but according to your definition, if the value is 0, then P1 loses. So even if we are in some other state,
Yeah.
in any of these steps, the DP value 1 denotes that P1 will win, whether it's person 1's chance or person 2's chance.
Yeah. Whosoever chance it's right now, he will win or lose. That's what we are saving.
Oh, he will win or lose, not person 1.
No. Person
Okay.
1. So person 1 is, so we are not going about global scope. So that's that. So person 1 and person 2 will move first and second. That's okay. But like we say that at a particular I, person 1 means like who is playing first. That's it. And we will just call dp of like the actual n input as the person, like for that we can get which is the person 1 or person 2, and that's the answer, right? So when we are defining, we are saying person 1 and person 2 with respect to that particular move, and then for the answer we are saying that okay, the original person, right? And
Okay.
in general, like yeah, that's the whole thing. So complexity wise also, I think Saurabh, that's correct, because like for there are n total states, and on each of the state you might need all the m transitions. So this is going to be order n into m. Is this clear to everyone? Can I have a +1 if this particular question is clear? I think one of this question is there in the like, practice problems from in the external problems sheet, so you can have a look at that. Okay. So if you even try to fill up some values using this, let's say like if you just try to validate what we said, okay, n equal to 8 and dp of, so that moves were, let's say 1 2 3. So if we try to fill up the values of dp, like I'm just quickly doing it on an array, an iterative styled array, okay. So like initially it's 0 for 0, okay, then on 1 you can take 1 and you can go to 0, so that is going to be winning. For 2 you can take 2 and you can go to 0, so it's going to be winning. It's losing for opponent, so you're winning. From 3 you can go to 0, so that's going to be losing for your opponent, so you are winning. But from over here there are 3 moves that you can do, but whichever you do, the state you are going to is going to be winning for opponent, so you are losing, okay? And then this will repeat. So that's why for every mod 4, like every like I mod 4 equal to 0, it will be losing, like 1 1 1 then 0, then 1 1 1 0, so on, right? It will be periodic. And in fact a lot of such subtraction games are always periodic, okay? So periodic property in games are very common, okay? So people, like when we will see actual game theory, we will look into this kind of properties, but it's something you can have a look at, okay? Okay, so if this is clear, then that's all I had for this particular session.